Welcome everyone. In this section, we're going to go into dimensionality reduction. Specifically, this is in the realm and in the area of unsupervised learning now. We have moved away from supervised learning, whereby you have a target variable or your classification data has a labeled data, or the regression has actually a target variable for your machine learning algorithm to learn. We are moving to a completely different realm whereby we are trying to discover bad pattern and trying to discover some sort of consistency or relationship within the actual data itself. We don't no longer working with a target variable, and we've moved away from that. So that's really where dimensionality reduction comes in. It's trying to actually identify some of the key components. Also, the other word is called factor. Right, the first method that we're going to look at is called principal component analysis. Now, this is a concept that is borrowed from statistics and has been around for a long time. How does it work? It's basically a linear dimensionality reduction using what's called a singular value decomposition of the data to project it to a lower dimensional space. I'm not going to go into and explaining how the singular value decomposition works, but I will actually illustrate it a little bit later. It's basically a statistical procedure that utilizes what is called orthogonal transformational technology. Ultimately, what we are interested in is what comes out at the other end. It basically converts possibly correlated features or predictors into what is called linear uncorrelated features. And these linear uncorrelated features is called principal components. The number of principal components is usually less than or equal to the number of features or predictors. Now, you probably will recall, I hope that you've gone through the regression section, whereby there are a lot of components. When we actually plot the scatter plot, there were a lot of the features that relate to each other or have high correlation of more than 0.5. And that really is the idea here with principal component analysis, is that it's trying to remove, first of all, takes out a factor that drives both the features, meaning go back one step and look at what drives the actual feature itself, and then from there it looks for what's called uncorrelated features. So that's really how principal component works. Typically, the first principal component explains the largest possible variance, so it will have the greatest contribution to the variability or the variance of the underlying data. Each subsequent component has the highest variance, subject to the restriction that it must be orthogonal to the preceding components. Now, orthogonal is a very intimidating word. I guess the other way to look at it is when you go back to your high school math, if you think a little bit about Pythagoras theorem, remember that the triangle must be right angle. So let me just try to plot it out for you here. Remember this, okay? And you will have a right angle here. This is the triangle or right angle triangle that's usually called, and this is 90 degrees. Okay, and likewise, if you look at the geometry space, not a triangle, you will actually have something that looks like this. So if I have a line that is like this, what is orthogonal to this line? It will be something that looks like this. Okay, I'm sorry if my drawing is not perfect. This is not my day job, neither is it my hobby either. So if you look at this, so this is 90 degrees. Okay, so that's really, let's just call this PCA1. That's our principal component 1. And the second component here will be called PCA2. And this part really is what the orthogonal means. The subsequent components has the highest variance subject to the restriction. And what is the restriction? It must be orthogonal to the preceding component. So the PCA2 must be orthogonal to PCA1. What about PCA3? Unfortunately, this is the tricky part. I can't show you because we are starting to go into a three-dimensional space now. So at the very least, on the two-dimensional space, you have an appreciation of how it works, and hopefully you can actually borrow from that abstracts and go a little bit further from there and understand that orthogonal basically means that it is right angle in the geometric sense, but in the intuitive or common sense, it's basically has no relation to. So meaning is independent, or when you actually use a statistical measure such as correlation coefficient, basically it means zero. Okay, I hope you got that. I'll try my best, and that's really the basic idea of how PCA works. So the collections of all these components are called vectors, but there's one thing about PCA that you need to bear in mind if you're going to use it, is that it is very sensitive to scaling. All right, the second dimensionality reduction tool that is commonly used is called linear discriminant analysis. Sebastian actually has written a really nice blog on this, so I encourage you to actually go and read through that. It is very commonly used as a dimensionality reduction technique, as I mentioned, in the pre-processing step for pattern classification and also machine learning application. The goal here is to project a data sets into a lower dimensional space with good class separability in order to avoid overfit and also reduce computational costs. The other way to explain this is that what the linear discriminant analysis is that it actually locates the boundaries around clusters of classes. Okay, so basically it's trying to identify where the boundary lies between 2 or 3 classes, and then it projects these data points onto a line, and the whole idea is that it's trying to actually keep it as separate as possible. Now each cluster, a centroid will be allocated to each cluster or have a centroid nearby. So I guess the other way to put it, as Sebastian quite nicely has placed it, with PCA, what happens is that you have the component axes that maximize the actual variance itself. Whereby for LDA or linear discriminant analysis, it maximizing the component axes for class separation. So that's really the basic idea of LDA here. Now there are other dimensionality reduction techniques. I'm going to list them here, but I won't go through them. I'll just list them here so that you are aware of them. If you want to understand more, please do feel free to explore. But for my part, I won't be actually going into these more complex dimensionality reduction techniques. Most people use either PCA or combination of PCA and LDA, and that's sufficient for their use. So a couple others is MDS, whereby it seeks a lower dimensional representation of the data, whereby ISOMAP, again, also seek a lower dimensionality embedding. What happens is that it maintains the geodesic distances between all points, and also TSNE, also T-distributed stochastic neighbors embedding. This is a non-linear dimensionality reduction technique. Okay, right. I guess one of the main thing that I do want to go through, but this is only very briefly, for those who are very familiar with linear algebra, you don't really have to, you can actually pause now and or finish off this portion of the video and move on to the next video, which is diving into principal component analysis. I just want to use this opportunity just as provide a refresher, because PCA does make use of a lot of linear algebra or matrix multiplication. So I'm just going to demonstrate that a little bit. Okay, so all right. So let's just say, okay, you have two variable, two matrix. A is equal to that and B is equal to that. You want to multiply A multiply B. So they are both 2 by 2, 2 by 2. So multiplying them would not be any issue. But how do you actually multiply them? In essence, what happens is that you have 1, 2, all right, will multiply 1, 100. Meaning 1 will multiply 1, 2 will multiply 100. So that will form your first top left cell here. Okay, the next one will be your 1, 2 will multiply your 2, 10. And that will form the next cell here along the actual column, row itself. So it's 1 multiplied by 2 and 2 multiplied by 200. The next one will be taking, you take your 10, 20, multiply by 1 and 100. So that would be 10 multiplied by 1, 20 multiplied by 100, and on it goes. So that's really to illustrate to you how it works. The other part that I do want to actually illustrate is that how does this work when you're using NumPy. This is for those who are not familiar with the NumPy pandas. So I'm just gonna do this. So all right, so you have your AB, which is here. All right, A, the first row is 1, 2, second row is 10, 20. Okay, 1, 2, 10, 20. B is 1, 2, 120. So this is the representation of the matrix itself. So I'll have a look at A. This is what it looks like, and B, this is what it looks like. Now with NumPy, it's actually built-in so-called, we don't need the whole thing. There is a built-in matrix multiplication. Okay, so it's just NumPy dot A and B, and when you run it, you will notice that you actually get this answer that we already presented here. So that's really a really quick refresher of linear regression and matrix multiplication. That's pretty much the end of this lesson. I'd like you to actually just refresh yourself a little bit with the idea here called dimensionality reduction. Why we do this is because quite often we are faced with large data sets and many features, and sometimes easily 200, 300 and maybe up to 1,000 features, and it's difficult to actually and quite often there are two reasons here. One is that it's really hard to train a machine learning algorithm with 100, 200 features. And second thing is that it takes forever. So hence we actually use PCA or LDA, just do some dimensionality reduction first before we actually start training our model. Okay, both of these methods will preserve the actual feature, the key features of the key components, so that there are not a lot of contents that has been lost. With that, that will be the end of this lesson. Thank you for watching. I look forward to diving deeper into principal component analysis next.